Hello everyone, hello my dear students. I'm here with you. This is your teacher. Before we start in physics for the next lesson, I just wanna tell you a reminder that now in YouTube there is a page, and that page for the science subjects for Pyramids American School. You will find the page on Facebook, Pyramids American School Science. This is the page now. Please subscribe and all the time view your videos. Do not postpone your classes. And let's talk about our lesson for today. So we're talking today about the waves. So this is gonna be the last lesson at the waves. First, let me remind you with period, frequency, and wave speed. So, speed of a mechanical wave is constant for any given medium. Remember that the speed of the wave is given by the following equation, which we already took on class before. Is that the wave speed is equal to frequency multiplied by wavelength. Just a kind reminder that wave speed, its unit is meter per second. Frequency, its unit is hertz, and wavelength, the unit is meter. This equation applies for both mechanical and electromagnetic waves, and we are concerned about the wave as waves and sound waves. So waves and energy transfer. Wave actually transfer energy by vibration of the matter. Remember, there were two types of waves that we talked before in class, longitudinal wave and longitudinal wave and transverse wave. Longitudinal wave and transverse wave. Wave actually also are often able to transport energy efficiently. The rate at which a wave transfers energy depends on the amplitude. Remember the amplitude. The greater the amplitude, the more energy a wave carries in a given time interval. And remember that the amplitude is how far you are from the equilibrium point. Whenever we have a pendulum, how far we are from the pendulum point. Also, amplitude of a wave gradually diminishes over time as its energy is dissipated. So I want you today to apply the superposition principle, differentiate between constructive and destructive interference. And it's easy to differentiate between them because one of them is building and one of them is destroying. And I want you to be able to predict when a reflected wave would be inverted and predict whether a specific traveling wave would produce a standing wave. So, for wave interference, before I show you the wave interference, I just wanted to share with you a video for an example of a wave. And that video, for example, of a wave was actually by the singer Amr Diab. You can see here, he's carrying a rope and he's trying to show his muscle. See, what Amr Diab is doing with the rope is a wave. He's doing with the rope at the gym a wave. This is exactly what I mean whenever we talk about wave. So he's doing now a different wave, but we are concerned about the first type of the wave. So, mechanical waves are not matter, but rather are displacement of matter. Two waves can occupy the same space at the same time. Actually, combination of two overlapping waves is called superposition. As you have seen in the video before, Amr Diab was carrying two ropes at his two hands. Each of his hand he was carrying a rope, and he was throwing who's doing two waves together. So now we're going to talk about like two waves that occupy the same space at the same time, and when those two waves are doing a combination or overlapping of those two waves, which is called superposition. So in constructive interference, if we have two waves, so one of them you can see here a big wave and a small mechanical wave, they are coming together. If they are coming on the same side, they are both on the same side, look to the peak is actually going up, both of the peaks are going up. Whenever they meet each other, they build something called constructive interference, because both of them on the same side. As a result, the peak of the wave, or the amplitude of the wave, is going to increase more. So it's going to be the summation of the two peaks, and after that it will continue and each of them will move to the other side. So see, the small peak was going from this side, and now there is like going on the other side. So for destructive interference, and this is a difference between constructive and destructive, in destructive interference the two waves are going opposite to each other, they are in opposite sides. One of them, see the peak on the top, the other one the peak on the bottom. When those two waves are going and meeting each other, their resultant wave is gonna be not the summation, it's gonna be the subtraction. So the bigger wave, which is the one on the top, will be dominant. So the resultant will be the amplitude of the big wave minus the amplitude of the small wave. And afterwards they continue. So when we talk another thing which is called reflection. So reflection is whenever you have a rope and you carry it with one hand. You have one rope, you carry it on one hand, and the other one you put it on the wall. So to put it on the wall, you call the wall a boundary. So a boundary is whenever you carry the rope from side and on the other side to the wall, this is called a boundary. So for your boundary, there are two types of boundaries. One is called free boundary. Whenever you are at your rope to the wall, you are like doing a circle around the wall. So your rope is not fixed to the wall. This is called free boundary, because the rope has the ability to move up and forth, up and down, up and down. But for the fixed boundary, your rope is fixed to the wall. So your rope won't be able to move. Whenever you move it, it's gonna be stuck to the wall. So see, the free boundary, the rope can move, and the fixed boundary, the rope is fixed. So the difference between them, that at the free boundary, waves are reflected, which means that, sorry, this keeps going up. So at the free boundary, waves are reflected. So that means that whenever the wave is going on this direction, it's reflected on the same direction. See, it was up, it's returning as up, because this is free boundary. But for the fixed boundary, the wave are reflected and inverted. So not only they are, when they hit the wall, they are reflected, but they also was being reflected, which means that they are turning back. The wave changed its position. So instead of having the peak to the top, now the peak to the bottom. So you can see the reflected pulse, it is inverted, and this is the condition of the fixed boundary. Standing wave. Standing wave is a wave pattern that results when two waves of the same frequency, wavelength, and amplitude travel in opposite direction and interference. Now you have the two waves, your two waves, they are meeting each other, but those two waves have the identical frequency and wavelength and amplitude, and they are in different position. So at that situation, a node is called as a point in a standing wave that maintains zero displacement, and an antinode is a point in the standing wave halfway between the two nodes at which the largest displacement occurs. To see the node and antinode, remember, node is zero displacement. Antinode, it is at the middle between two nodes, and it has the largest displacement. See here, this is your length, and there is, like here, those two on the end are called nodes because they have zero displacement. This is only one wave. When you have two waves meeting each other, see what happens? When they meet each other, there is node here, node here, node here, because those are zero displacement. And at the middle between each of two nodes, this is called the antinode, which has the largest displacement for the two waves that meet each other. Remember that the ends of the string must be nodes because these points cannot vibrate. Whenever you have two waves, those two waves, you can see they are different. So this is a kind of wave, this is a kind of wave, this is another kind of wave. So all of those three waves are different, and each of them has different frequency and different amplitude. Standing wave can be produced for any wavelength that allows both of the ends to be nodes. Now look and let's try to think about this. So the wavelength for B here is called 2L. Do you know why? Because actually those two wavelengths, this is whenever those two waves are meeting, the wave, the peak will be here, the other one, the peak will be here. So this is a peak, this is a peak, we call it a thrust. We said before in class that to be able to get the wavelength of a peak, you have to have two thrusts at the same position. So this one on the top, this one on the bottom, there will be another one out of the scope here on the top. So the distance between two top thrusts together, two consequent top thrusts together, will be the wavelength. So for the case of B, the wavelength will be 2L. So it's not only 1L, it's gonna be 2L. And the case for B here, this is B. This is 1, and this is 1, and this is 1. So B here will be 2L. So this is B. 1 here is a peak thrust. To have another thrust, the second one will be on the bottom, the third one will be a little higher. So the wavelength will be 2L. But here at C, the conditions of C here, your thrust 1 will be here, the other one here, the second one will be here. So between those two consecutive thrusts, your wavelength will be equal to L. Now the third situation, which is D, between two thrusts, which is gonna be here, and this is here, and this is here. So once you get the distance between those two, the thrust here and the thrust here, because they are both in the same position, third one is on the bottom. So once you get the distance between those two, you'll be able to get the lambda. And to do that, it's easy. You just have to divide the length into each of those units. So for example, all of this one is called L. And how many parts of L do we have? All of this from the beginning to the end is called L. So this is one part. This is equal to this part, number 2. This is equal to this part, number 3. This is equal to this part, number 4. This is equal to this part, number 5. This is equal to this part, number 6. So each of those is called L over 6. And to get the distance between here and here, it's gonna be 1, 2, 3, 4. So it's going to be, as we said, 1, 2, 3, 4 out of 6. So it will be 4L over 6. So 4L over 6 is equal to 2L over 3, which is lambda. Now try to do this again with here. See the rope here? It's the length, the total length is called L. So to be able to get the wavelength, the peak here, now let's divide it two parts. This is 1, this is 2, this is 3, this is 4. So all of them are called 4, or each of them is 1 out of 4. To be able to get the lambda, it's gonna be 1, 2, 3, 4. So it's going to be 4 over 4. So 4L over 4, it's gonna be 1L. And this is how we can get the wavelength. Now, for the standing wavelength, as we said before, this photograph shows 4 possible standing waves that can exist on a given string. You can see here, this is case at the beginning, this is case B, this is case, also this is called case C. So this was B, this is C, this is D, and now we even have a case here that we can call it F. And now let's try to do that division thing. It's gonna be 1, 2, 3, 4, 5, 6, 7, 8. So each of them are called, so all of the total is called 8. And now to be able, if this total length is L, to be able to get the lambda, it will be between this peak and this peak. So it's gonna be 1, 2, 3, 4. So it will be 4L over 8. So as a result, that new one at the end, to be able to get the wavelength of it, it's gonna be 1, 2, 3, 4 over 8. 4L over 8. So its wavelength will be L over 2. With that, I want to finish, and I wish you all to be doing great at those conditions. Please subscribe to our page on YouTube. Thank you all.